learn the structure causal model from this unfair data, and then we want to like modify it and generate a fair synthetic data, so that can be used in the maybe in some downstream task. Okay, so this is there's one paper, DCAF, generating fair synthetic data using causal level generative networks. They address this problem. That is, they generate fair synthetic data from the unfair data by learning underlying data generating process with GAN training on tabular data. So what type of fairness they address? So suppose we have some like random variables or distribution from P of X, some protected or sensitive attribute A, and the target variable Y. So conditional fairness, they are saying that is the predictor Y hat is said to be conditionally fair if the sensitive attribute A is conditionally independent of the prediction Y hat given R. So it's like suppose so A is independent of Y hat given R. So you can think of R is some population, and it's in that subpopulation we want the prediction to be independent from this sensitive attribute. For example, if we think like A is the sensitive attribute, that's suppose like race, and race of a person, and R is maybe some subpopulation, maybe from a area or a country or some area. So we want this is okay, in that area the model prediction has to be independent from this specific race of that population. So that means the R equals to R is fixed, that means that area, but when A equals to A versus A equals to A prime, both prediction has to be same. That means this A has to be independent of Y given R. Now, so what? How do they do that? So they generate features, generate like sequentially following the topological ordering of the underlying causal DAG that I mentioned. That's like they perform ancestral sampling, and so this is the architecture they follow. That means like suppose GI is some GAN, and then they first generate the root variables in the causal graph, and then they feed that value to their children and so on. So these parents are also generated, and they feed some Gaussian noise or uniform noise to this GAN to generate this corresponding variable. Now, if you see here, like they will do like generate fake data. Here I have like 5 variables, and so I have 5 GANs, and each of these GANs will take their parent variables and some Gaussian noise and generate their corresponding values. So I have 5 variables, I have 5 GANs, I have like 5 different values. These are fake data, and I have like real data also in our hand. So I compare this fake data and real data with a discriminator. This is a discriminator loss function, and that will give me the loss objective to train this model, train this architecture. So here we are again by like comparing real data with fake data, we are learning this structural causal model. Now what? So here this was our goal, right? Like A, the sensitive attribute has to be independent from Y given like R, the subpopulation, like some other variable. So now suppose R is equals to C, this variable. No, that means so now if I condition R on C, this path A to B, B to C, C to Y, that path is blocked, right? Like you saw, like it's dissipated. That means the correlation or the dependency between A and Y cannot pass through this path. So only paths open is A to Y directly and A to B, B to Y. So that means like when R is C, that means when we condition R, this path is already blocked. We have to perform intervention on this edge and this edge. Similarly, suppose B is the R variable, that means B is conditioned on, then this path is blocked, this path is blocked, we have to only intervene on this edge. So here we have to just intervene on this like red edge. So how do we intervene here, like how we are dealing that edge? It's like some kind of surrogate intervention, that is here the prediction should not actually like when for a specific value it should not depend on A that much. Like for predicting Y, it should not depend on A, or like how the A variable is looking like. So what we can do is like we can just like uniformly sample these values like B and C, the like conditioning variable. We can uniformly sample that, and we can see like we can do the inference, and in the inference stage this prediction will be independent from A given R. So the main message is like we can delete the edge by uniformly sampling this value. Since Y is not seeing any specific extra proportion of that A anymore, it's like seeing it like uniformly, so it will not be biased towards that protected or sensitive attribute. Okay, now next let's think of like the second another problem, how we can deal with this setup. So can we use neural networks to understand if a causal effect can be estimated uniquely from given observational data? That is test identifiability. So identifiability is like, I heard there's like one question that is, okay, we cannot estimate the causal effect uniquely, but can we get a bound or something? Or like, can we, how can we use identifiability? That's okay, can we actually estimate the causal effect or not? So the question here is not bound. The question here is, do we have a specific unique causal effect, or do we have multiple causal effect that we are not sure which one is the true causal effect? So if so, can you obtain the estimate at the same time? Can you use neural network for this purpose? So there's this paper, the causal neural connection, expressiveness, learnability, and inference. This paper deals with this problem. This paper follows the same architecture proposed by causal GAN. That means like you use one neural network for each variable, and then you do ancestral sampling,